Hello and welcome to this week's lab report. We continued working with constant acceleration. However, we looked at an inclined plane where our cart accelerated going downhill. We observed how the acceleration would be affected if we change a glide's mass, which in reality it really won't by much. But we also measured the acceleration and compared it to the theoretical one. This, pa- this paper's main purpose was how to show students how to confirm the relationship between gravitational acceleration and incline angle. Its overall main results showed that gravity is dependent on angle of inclination during its sliding experiment, and it also mentioned how friction may also be accounted and measured in order to improve accuracy in experiments like this. Remember that a steeper slope increases acceleration. A good reference are ramps for individuals with disabilities that may require a wheelchair or older individuals who are limited in terms of mobility. These are designed with a specific slope or more specifically 1 inch of rise. For every 1 inch of rise, there should be 12 inches of the ramp length to ensure safety. Really, this example further emphasizes that acceleration is not dependent on mass, but rather the angle.
The materials that were used for this experiment were the Pascal/Capstone application software, and this application software was used to generate the graphs that will be presented later on. An air truck, glide, and weights were utilized, and the air truck was used to create the motion as information was being recorded. The glide served to facilitate the grip, to push the glide and create the motion. Four weights, including two small ones and two large ones, were used to incline a plane. A passport motion sensor was used to record the motion as the glide approached and backed away, leading to creating of the graph. A laptop scientific notebook were used for observations that will be presented later on in this video, such as calculations.
For the procedure, firstly, we calculated the theoretical accelerations of the cart on an inclined plane in order to use later on. Then we performed the experiment, first with the height elevated and with the cart itself. The second trial was with the same height but weights added onto the cart, and the last trial was with a different lower height and the cart by itself. The next step after performing the trials, we calculated the experimental accelerations and other values, then compared them to the theoretical values and calculated any percent errors found.
This is data and data analysis for Lab 5. To start this lab, we found the theoretical acceleration first using our measurements. So gravity is 9.81 meters per second squared. Our sign, the way we find that is the opposite over hypotenuse. And then our height are the three pieces we were given. So we measured the height of those three pieces together and it was 4 centimeters. Then we changed the centimeter units to meters and it was 0.04 meters. We created the triangle and our hypotenuse was the 1 meter or the 100 centimeters. And then because it's our triangle, the angle was here. So opposite was the height, and our height was the zero point 0.4 meters or the 4 centimeters. And then using that triangle, we found the sine of the angle of our track. So that was the 0.04, because again, it was 0.04 divided by the 1 meter. And then using that, we found the acceleration of 3.924 meters per second squared. So following our procedure, once we added the height and changed or put turned on the sensor and put the glider, like this is the slide, and then from here we put it at the halfway point rather than starting at the very, very top. This is the graph we got. So because it's not like moving like a traditional position versus time graph and it has spikes, that's incorrect. So we had to do it again. So after a couple of tries, this is the graph that we got. And then this is the graph that we used for our first section. So using that graph, we went ahead and created, from our position versus time graph, we created the velocity versus time graph, and then we annotated some points. Our points were 2.650 seconds with our velocity of negative 0.5 meters per second because it was going down. The position versus time graph was going down, so the slider was going towards the machine, towards the sensor. And then our second point was 5.7 seconds with a velocity of 0.6 meters per second. And that just shows that, again, the glider was going away. So position versus time graph shows it was increasing, and it's a positive velocity. So using the previous graph, the points we had found in the velocity given through that, we found the initial velocity of 0.57 meters per second and then our final velocity of 0.6 meters per second. And then we found that's our expected acceleration, which was 0.3924. And then using what we had found, the velocity, we found the acceleration. And the acceleration there was 0.38 meters per second squared. And so our percent error, the difference between the 0.3924 that we had found and then the 0.38 that we found using the velocity versus time graph that was given by the sensor, it was a percent error of 3.16. So this is our glider without any weights or anything. We were just using the actual measurements from the graph that we created. And we are expecting a similar acceleration for when we do add the weights. And we're hoping for practically no change because our acceleration isn't supposed to be changing even if we do add the weights or the mass. And then our percent error, we hope if it does change any, it will be small. So that way we created as close, our readings from the sensor is as close to what we had theorized. And then this is our table 3, our experimental acceleration 2, and then the high mass and high tilt. So it's still a high tilt, and then now it has a high mass as well because we added the weights to the sides. And then using the measurements that we had gotten from the graph, this is negative 0.6 meters per second, we found the acceleration again from the formula of the final minus the initial divided by the change in time. And then that was 1.07 over 2.7. And when we divided that, it was 0.39629. So we went ahead and rounded that to 0.39 meters per second squared. And then our percent error was 0.6. Or 0.611, but we went ahead and rounded that as well to 0.6. So we believe our percent error was slightly different because the weights, what was interfering before, like maybe the glide could feel like more of the air shift and the vibrations would be picked up by the sensor. With the weights, it's more steady and then therefore less friction and less things moving it around, causing less differences in our calculations. Following our lab for step 3, we followed the new change. So now instead of being the same tilt, it's a lesser tilt. So from being where it used to be 3 pieces that measured 4 centimeters, now it's just one big piece that measured 1.5 centimeters. So again, we did the same process we had done for the beginning of the lab. We created our triangle. Our hypotenuse was 100 centimeters or 1 meter. And then our angle, the opposite of our angle, was now the new height, which is 1.5 centimeters. 1.5 centimeters divided by 100 centimeters equals 0.015 centimeters. And then we change centimeters to meters, it's 1.5. So that's how we got the new sign of our graph, 1.5. And in using that amount, we went ahead and 9.81 times the 0.15, we found the 0.14715, which we rounded to 0.15 meters per second squared as our theoretical acceleration. Our percent difference was 6.17, which is bigger, but also because we are changing the measurements. So it went from traditionally 4 centimeters as the height to 1.5 centimeters height. So that's a difference. And then because of that, our values are, of course, going to logically change. And then this graph is what we used, or what we got from when we changed the height. And then again, we annotated it and found the velocity versus time graph. And our points used was 3.35 seconds at a velocity of negative 0.4 meters per second. And then our second point was 8.2 seconds, and our velocity was 0.36 meters per second. So using our second graph, the one that we had previously shown, and finding those points, we found the new acceleration via the formula final velocity minus initial velocity divided by the time change. So our acceleration using the graph was 0.16 meters per second squared. The theoretical that we had found previously was 0.15. So the difference is 0.01 of our accelerations. So our percent error is relatively small. And when we found our percent error, it was using the formula, the theoretical measurement minus our actual measurement divided by the actual measurement and then times the 100. So we found the 6.25% error. It's just relatively small, and it's just following what we had originally found. It was very, very close to what the graph gave us, our acceleration.
In this lab, we measured the acceleration of a cart on an inclined plane and compared it with theoretical acceleration calculated from Pythagorean theorem equations. Our first setup with a steeper incline gave us an experimental acceleration of about 0.39 meters per second squared, which closely matched the theoretical value with a small percent error of around 3%. When we added mass to the cart, the acceleration nearly stayed the same and barely changed. So it went to 0.30 meters per second squared, and we got a 0.6% error, which confirmed that acceleration due to gravity on an incline does not depend on mass. When we reduced the tilt of the track, both theoretical and experimental accelerations decreased significantly to around 0.15 to 0.16 meters per second squared, and the percent difference rose to 61 to 67%, which is likely due to smaller angles, which amplify measurement and friction errors. So the steeper the incline gave us greater acceleration. Overall, the experiment supported Galileo's observation of acceleration on an inclined plane. Thank you.